We're going to begin Unit 7 by looking at something called stoichiometry and introducing what that is. Now, the word stoichiometry is probably brand new to you, probably never really heard of it, have no context for it. So it's important, again, that we get into that. But before we do, just a quick overview of the unit. We're going to be looking in Chapter 9 of your textbook, so feel free to follow along there. We'll also be looking at some of these topics here. We'll cover the first three in this, or at least in this set of slides. And the last two topics will be covered in another set of slides. All right. Before we can talk about what stoichiometry is, let's make sure we review the mole. Now, I think all of you should remember what the mole is, sort of. So let's go ahead and review that real quick to make sure we remind ourselves. First of all, the mole is a unit that represents large numbers of small particles. Effectively, it's a way to count large numbers of particles without actually having to count them out. It's representing large groups. Particles, of course, that word is very broad and it can mean anything like molecules, formula units, atoms, electrons, so on and so forth. More often than not, we'll be talking about atoms and molecules. Don't forget also that there is this number associated with the definition of the mole, known as Avogadro's number or Avogadro's constant, and we're looking at 6.022 times 10 to the 23 particles per 1 mole. In case you kind of need a refresher on exactly what the mole is like, there are a couple analogies down here that you can use. First of all, a dozen is used to represent 12 particles, so you say 12 particles per dozen here. Right. Or a score is used to represent 20 particles, so 20 particles per score, so a number of particles per this new unit. And the mole is the same way. A mole is used to represent 6.022 times 10 to the 23 particles, which you can see also represented right here as 6.022 times 10 to the 23 particles per 1 mole. Another concept that's very much relevant from the past and also going to be used here is called the molar mass. This is the definition where it says the mass of a mole of a pure substance. This is definitely something that we've probably forgotten, but we're going to be using it quite a bit in this next unit. A couple of examples of molar masses. Don't forget that the numbers here, lithium, for example, is 6.941. Remember that there's going to be a certain set of rules to how you take the numbers off of the periodic table. Generally speaking, what we do is we like to either take 2 decimal places or 4 numbers off of the values, whichever one gives you more to work with. So lithium, let's go ahead and take a look at that real quick. With lithium, we're going to see that it's over here. Right? So you have 2 options. It can either be 2 decimal places, which would be 6.94, or you could have 4 digits, which will be 6.941. And we like to use the one that gives you more digits to work with. So it turns out the second value is the way to do it. So using 2 decimal places is too limiting, so we use the second one instead. So we use 6.941. We can also do the molar masses of compounds, which you see here. Carbon dioxide has CO2, and we do that by taking the numbers of each element and distributing how many each element there are and combining them. So for carbon dioxide, you have 12.01 grams per mole, right? That's the molar mass for just carbon. Then we also have the 16.00, but so on and so forth. That corresponds to oxygen. And then we add those up. Don't forget that there's 2 oxygens because that comes from the CO2 subscript next to the O. Combine them and you get 40, well, technically it's actually 44.01. But again, not super important, but do know that that number, again, comes from the sum of all the molar masses there. How do we apply molar mass? One thing, of course, is getting the molar mass is good, but we have to know how to use it. So in this case, the question asks, how many moles are in 55.83 grams of carbon dioxide? So let's remind ourselves of how this works. We have carbon dioxide, that's our substance, and we're given a gram amount, right? So we're given a mass. And then we're being asked to figure out moles. So we're going from mass and trying to convert them to moles. How do you relate mass and moles? How do you relate mass and moles, or moles and mass? Interesting. Oh, I know. How about molar mass? Conveniently enough, since we're working with carbon dioxide, that's the same value that we got from up here. So let's go ahead and apply that. We're given 55.83 grams of CO2. We apply the molar mass as a conversion factor, so that 44.01 grams of CO2 for every 1 mole of CO2. All right, it's been a little while since we've seen these kind of problems, but don't forget, right, whenever you see this whole thing right here, this is the entire molar mass that you used from before. And don't forget, when you talk about grams per mole, right, it's not grams per mole that are on the bottom of the equation, right, because then actually this mole is really up here. So when you do these, make sure you have the mole on top and then the gram on the bottom. Right? Try not to make it mix and match and force extra units where they don't belong. All right, so that's why we have grams per mole like that, not grams per mole all crammed in on the bottom here. All right, so that's not okay. All right, so that's basically it, right? Make sure you do the math. So 55.83 times 1 divided by 44.01, and you should be getting somewhere around 1.329 moles of CO2. And don't forget, we are also going to have to look at significant figures and such, but we can deal with that later. One more thing to consider, chemical formulas in the mole. This might be something you remember from a while back, but a long time ago, remember, we didn't have formulas that were just given to us. We had to figure those out ourselves. And when I say we, of course, that means, we're talking about scientists from historical parts of the world, and making sure that they could calculate and make calculations to figure out the formulas. And so one of the things that they could use was the mole ratio. Now, if you remember, there's something called empirical formula problems that we did. Those empirical formulas, the reason why we could get numbers that go next to the letters, like for example CO2, where do those numbers come from? Well, it comes from those ratios. So we know today that those formulas for carbon dioxide, we get that formula because they figured out the mole ratio between carbon and oxygen was 1 to 2. So that ratio, the mole ratio, if you look at a sample of CO2, the C is a 1, the oxygen is a 2 because it's a 1 to 2 ratio. So one of the big things you can take away from this is that you can also know that the atom ratio, right? So the single compound itself is made of a single C. It's got a O's on either side. And so that's a 1 to 2 ratio. So if my particle ratio is 1 to 2 between carbon and oxygen, that means my mole ratio between carbon and oxygen is also 1 to 2. And that's where this line really becomes kind of useful to keep in mind. So the ratio of the particles is equal to the ratio of the moles. Now, this is specific to chemical formulas. We're going to see in a little bit how that's actually applicable to equations. All right, so the ratio of particles, again, is equal to the ratio of the moles. All right, so now is where we get to actually see stoichiometry in action. Don't forget to give yourselves a couple of seconds here to practice the word stoichiometry. We use it quite a bit, and I want you to feel comfortable saying that. All right, so what exactly is it? It is the application of quantitative relationships in a chemical reaction, the Greek word stoichion, which means element, and requires a bit of information from previous stuff like moles, molar mass, nomenclature, and chemical reactions, all of which we have worked with recently. So let's make sure we can interpret chemical equations. This is one that, just an arbitrary one, it's got C3H8, it's got O2, CO2, and H2O. And of course, we have to write it out so that they're balanced because they have to observe the law of conservation of mass. So by writing the coefficients in front, you can see that we have a 5 here, a 3 here, a 4 there. But what helps make a little bit more sense is seeing the number of particles actually present. So we only have 1 of these, 1. 5 of these, all of this, 3 of these, 3 here, 4 here. So these are basically used to not only represent the number of, or to make sure they balance out, but also it's nice to see them actually written out and drawn out. So you can keep track of the number of atoms on each side and also the number of compounds on each side. Now, one of the important things I want you to be able to recognize is that these are actually, those numbers in front are not just random numbers. In addition to, again, being able to balance, they also give us some more important information. So I want you just to be able to take what we know and sort of expand it a little bit. And this is a line that, is kind of not necessarily the most important one because it's, but it's got a lot of application because it's actually very similar to what I highlighted earlier. It says the coefficients represent relative mole amounts of each substance in the equation. All right, so the relative mole amounts. And really what that means when we talk about relative, we're talking about ratios, right? We're comparing them. These mole amounts are going to be compared. So relative mole amounts are definitely an idea that you want to take with you. All right, so let's go and talk about this. So we can say that for every 1 molecule of this compound, and you need 5 molecules of this compound, together they yield 3 molecules of CO2, right, and 4 molecules of H2O. So 1 molecule, 5 molecules, 3 molecules, and 4 molecules based on those coefficients there. And we know that because that visual from the previous slide shows us, literally there's going to be 1 molecule of the first compound, 5 of the next one, and so forth. But what if I expanded that, right? What if I said, instead of saying 1 at a time, let's say I do 1,000 at a time. What if I had 1,000 molecules of C3H8 and 5,000 molecules of O2, 3,000 molecules, and 4,000 molecules of those two? That kind of makes sense, right? Because the ratio between them more or less reflects the initial ratio of 1 to 5 to 3 to 4. So 1,000, 5,000, 3,000, and 4,000 again reflects the same ratio. If I expand that a little more, let's look at this first number, 6.022 times 10 to the 23 molecules. That's convenient. 30.11 times 10 to the 23 molecules, so on and so forth. Well, again, those numbers might not make immediate sense to you right now, but they're actually in the same ratio of 1 to 5 to 3 to 4, but instead they use the Avogadro's number, huge number of molecules. So if I have a huge number of molecules, how can I more easily count them? I can use the mole amount instead. And so what do you see here? 1 mole, 5 moles, 3 moles, and 4 moles of the substances. So it works out, right? Those coefficients here of 1, 5, 3, and 4, they reflect the individual particles, right? The individual compounds, but more importantly, and this is something you definitely want to be able to interpret, they represent the mole ratios between them. So for every 1 mole, 5 mole, 3 moles, and 4 moles of these substances, you can form a reaction. The particle ratio is equal to the mole ratio. Here's a quick analogy. If you want to give it a quick look over just to kind of help you put it together, this idea of comparing ratios, feel free to do so, but we can talk about this some more later. This gives you a chance to maybe get a better idea of how this works. Here's one more way that we can interpret chemical equations, and this is some language that I want you to get used to because this gets a little messy at first, but then once you kind of get the hang of it and you identify what's important, it's not so bad. All right, first of all, 1 molecule of C3H8 is going to react with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. Now, that looks pretty straightforward, no problem, right? What about the next line? 1 mole of C3H8 molecules will react with 5 moles of oxygen molecules to produce 3 moles of carbon dioxide molecules and 4 moles of water molecules. Okay, that's getting a little bit more wordy, or at least got a lot of words in there, but the message is again still clear. 1 to 5 to 3 to 4. Finally, 1 mole of C3H8 will react with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. So the difference here is that we're going from molecules to moles of molecules, right? And then finally, we're just going to simplify it to moles. So effectively, again, look at the ratios. 1 to 3, 5 to 3 to 4. That's effectively the same particle ratio as it is the mole ratio. Here's another set of ways that we can interpret it. To make 3 moles of CO2, you'll need 1 mole of C3H8. So let's kind of break this down. To make 3 moles of CO2, so 3 moles of that, you'll need 1 mole of C3H8. That goes over here. Now, that makes sense, right? Because, again, it's a ratio of 3 to 1. And the language here, let's be clear, too, is that we're not saying we don't need any O2 at all, right? I can't just literally make C3H8 become CO2. That's physically impossible. And, yeah, that means we have to have some O2. But the language really is just focusing on the relationship between these two. Right? Not saying that O2 isn't needed or not reacted or not involved. It's just not a focus of that problem. Same thing with the next line. 5 moles of O2 will allow 4 moles of H2O to be produced, right? So if I'm given an amount that's equal to 5 moles of O2, I could potentially generate 4 moles of H2O. Finally, for every 3 moles of CO2 that's produced, 4 moles of H2O will also be produced. So again, the idea is that we don't really necessarily say that the other substances are involved. We're just only focusing on those. So keep that in mind as you look at some of these other problems. Mole ratios, the coefficients is really the focus here, if you haven't noticed. That coefficient can represent the mole ratio between any two substances. So let's go ahead and take a look at this and identify 6 unique mole ratios that can come from this reaction equation. I'll start off by giving you a couple of them. I'll jot these in right now. So I went ahead and wrote 2 unique ones here. Let's start off with the first one. For every 1 mole of C3H8, there are 5 moles of O2. And do you see that? We have 1 and a 5 that corresponds there. The next one would be between 1 mole of C3H8 and 3 moles of CO2. Right, that's a unique one. Now, of course, some of you might be writing it the other way, so let me give you an example of that, where you just took the first one and flipped it upside down and generated that bottom one. And yeah, those are not really unique, right? It's just the same one just flipped upside down. So I've given you 2 unique ones. Go ahead and see if you can figure out the rest of the 4 of them. All right, so let's go put this into practice. This is the same problem that we've seen before. Let's go ahead and see how we can figure this out. If 2 moles of propane are burned, how many moles of water are also generated? So we're given mole amounts of this substance, and then we're being asked for moles of this substance right here. All right. Now, if we're being given moles of one, asked for moles of another, well, what can we use to relate them? Well, we have mole ratios, right? So if I'm given 2 moles, right, this is my given amount, so I always start with that at the top left here. I'm given 2 moles there, I have to figure out how many moles of H2O are involved, right? Well, how am I going to relate them? Again, that mole ratio is given to me in the problem, and I can just copy them directly straight off of what you see here. So again, I'll do this in blue just to make sure you know I'm getting it from, right? That's going to be a coefficient, and that's the other coefficient I want to use. Let's make that 1 and 4. That's all you have to do, right? So giving you information about one, you got to get information about the other, so that'll give you 8 moles of H2O as a result. Second one is kind of working the same way, right? If I'm given 7.6 moles of carbon dioxide, right, 7.6 moles of carbon dioxide are produced when some propane is burned. How many moles of oxygen were also consumed? So we're being given information about CO2, right? We're being asked about oxygen, how many moles of oxygen. Well, is there a way I can relate CO2 and O2? Yeah, absolutely. I can use the mole ratios, so let's make that happen. The mole ratio between these two is going to be for every 3, maybe if it'll show up, 3 moles of O2, or CO2, excuse me, right, coming from the coefficient here, is going to have a ratio of 3 to 5 moles of O2. And you do a little math, and using significant figures, around to about 13 moles of O2. All right, that'll do it.